All right, so last time we came up with this result, which we called the law of sines, and we solved two triangles. One was an angle-angle side, the other was an angle-side-angle triangle. And then at the end we said these are really two different variations of the same case, which is you have two angles and one side. But technically if you have two angles you have all three of them, so it makes life a little nice. But I promise this time we do something a little bit different. So given, this time we have an angle A equals 35 degrees. Then we have a side length, B is 15, and another side length, A is equal to 10. If we try to draw this triangle, say maybe angle A, down here, 35 degrees, and I'm not exactly sure where angle B or angle C are, but I can say, to be consistent with last time, we'll put angle B in the lower right, and so side length B will be opposite of that, which means something like this. And I don't really know how I can place the side A because I don't know angle C. But maybe logically I can say, well, if this is the base of the triangle, then if I close the triangle this way and say A equals 10, then I can do that. Now notice the configuration this time is an angle, then a side, and then another side. This is going to be the case when we have to think a little bit harder than normal. So we'll label this angle B, angle C, and side length C. We have two pieces of information that form this ratio. And we have a side length B, which means maybe we'll use this equality to try to find the angle B. So we'll write sine of angle A over lowercase a is equal to sine of angle B over lowercase b. The difference between last time and this time is that this time we're solving for a variable that's inside of the sine function. But if we isolate the sine function, we can say sine of capital B, multiply the b to the other side, which, if we substitute the values, lowercase b is 15, sine of capital A is 35 degrees, and then lowercase a is 10. We can punch that into a calculator and we'll get that sine of b is equal to, well, I'll say approximately equal to, 0.860. Now when we get to here, we remember that we spent an entire chapter discussing equations of this type. Sine of an angle is equal to a value. And we remember that that can have more than one solution. So we have to say, let's draw the unit circle and remind ourselves that the sine of any angle gives us the y-coordinate within the unit circle. So if we set the y-coordinate to 0.860, there are two locations in the circle where we can have the sine of angle B is equal to that, which means this could be angle B, but this could also be angle B. So we shall denote this B1 and B2 for the two different cases. So to find B1, we realize in the first quadrant, the angle B1 is the reference angle, which we can solve by saying B1 is the sine inverse of the y-coordinate. And when we punch that into a calculator, we get that B1 is approximately 59.4 degrees. But we also know that by symmetry, this angle B1 is the same as the reference angle of this triangle, which means B2 would equal 180 degrees subtract B1. In this case, B2 is approximately equal to 120.6 degrees. Now, let's put that in the context of this picture. The way I've drawn it, evidently I've achieved an acute angle. This is B1. This is 59.4 degrees. And we'll label C1 and C1 accordingly in this case. But how can I get that? Well, if I start by drawing angle A, like I did before, 35 degrees for angle A, and I say opposite of angle B, the side length B will be 15. This time, instead of drawing side length A so I close the triangle that way, I'm going to say, well, if I extend my base here, I could potentially close my triangle that way and say A is equal to 10. And in this case, I've achieved an obtuse angle. That angle is B2, and that's 120.6 degrees. Then the angle C2 is not the same as angle C1, and then the side length C2 is not the same as side length C1. So we're going to have to solve the entire triangle in two different cases, and we call these the ambiguous case because from the given information, we can generate two possible sets of solutions. So we figured out that there are two cases we have to solve. It's time to divide and conquer. In this triangle, we now have two angles, which means we can find the third angle by noting that the three angles in the triangle have to add up to 180 degrees, which means we can say that C1 is equal to 100 degrees, subtract A minus B1. We have A is 35 degrees, and we're going to use this as B1, which tells us that C1 is going to be 85.6 degrees. Now we have this angle. We can find the side length by saying we have the ratio here using the angle A and the side length A. We have the angle C now, it's time to find side length C. So we set up the ratio. We want to find little c, so we'll multiply little c over, and we'll multiply the reciprocal of this over to the other side. Lowercase c is equal to sine of capital C times lowercase a over sine of capital A. Now we'll fill in the numbers. This is sine of the angle we just found. And I should probably subscript all of these with ones. This is sine of 85.6 degrees multiplied by lowercase a was given to be 10 divided by sine of angle A was given to be 35 degrees. Now if we plug that into a calculator, we get that C1 is approximately 17.38. And there we have it. This triangle is completely solved. Now for the other case, we're down here. We have two of the angles. We can find the third angle by the exact same logic. We'll say A plus B2 plus C2 is equal to 180 degrees, which means that C2 is equal to 180 degrees, subtract the other two angles. We already know angle A is 35 degrees. That's the part that stays the same. And then angle B2 is the one we have up there. If we put in the numbers, we end up with C2 is 24.4 degrees. That's up here. The last piece of information we need is lowercase c to the side. And by the same logic, we have a ratio here, given. We have the angle C now. Let's find lowercase c. So we'll set up the ratios. And I'm looking for lowercase c2. Same logic. I multiply lowercase c2 over here, multiply by the reciprocal. We'll say c2 is equal to sine of capital C2 multiplied by lowercase a over sine of capital A, which means we can put in the numbers. Capital C2 is that angle, 24.4 degrees, multiplied by lowercase a, was given in the problem to be 10. And then sine of the angle A was given in the problem, 35 degrees. Then we put all of that into a calculator, and we get that lowercase c2 is approximately 7.19. So this is 7.19. And we have it. Both cases of the triangle have been completely solved. All right, let's look at another case. So this time, the given information, we'll have angle A is 51 degrees, side length B is going to be 12, and side length A is going to be 18. It looks a lot like what we were given last time. So let's try to draw a picture. We've got angle A at 51 degrees. Sorry, 51 degrees. This is angle A. And then we'll put angle B down here, which means side length B will end up right there. And once again, naively, I'll say, well, if this is the base, I can potentially close my triangle that way and make this side A is equal to 18 across from angle A. Then I'll call this angle C, angle B, and lowercase c. The given information, once again, angle, side, side in that configuration, which means we're going to have to watch out. So, I have angle A and side A, angle A and side A. I have that ratio. I have side B, and I want angle B. Let's do the same method. So we'll write down sine of angle A over side A is equal to sine of angle B over side B. Our target, angle B. So we'll multiply lowercase b over and say sine of angle B is equal to lowercase b times sine of angle A all over lowercase a. We'll fill in the numbers. So lowercase b was given in the problem to be 12. Sine of angle A was given in the problem to be 51 degrees. And lowercase a was given in the problem to be 18. So we punch this into the calculator, and we end up with sine of angle B is equal to 0.518. I'll put that as approximately equal to. Okay. Once again, we remember that sine of an angle equals the y-coordinate can have multiple solutions. We sketch the unit circle. The y-coordinate is 0.518, and there are two possible locations where we can have the sine equal to that. So as before, we'll label this as angle B1, and our other possibility is angle B2. If we close the triangle, we recognize that's the reference angle. That means B1 is sine inverse of the y-coordinate, which means, according to a calculator, that B1 is going to be approximately 31.20 degrees. Okay, we have ourselves a solution. But then we remind ourselves that we can close this triangle and say that that dot is the reference angle, which by symmetry is the same as angle B1, which means B2 would be 180 degrees subtract B1, right? 180 degrees subtract B1. And then the calculator says B2 is approximately 148.8 degrees. Now we have ourselves a problem. Because if this is 51 degrees, and that's 148.8 degrees for angle B, those add up to more than 180 degrees. So we actually know at this stage that it is no longer an ambiguous case. This is not a viable solution, because you cannot have the angles in a triangle add up to more than 180 degrees. Let's think about what that would look like if we tried to draw it. So if I tried to keep my angle 51 degrees for A, and I say side length B is going to be 12, and then instead of dropping the triangle that way, I want to think about putting side length A somewhere else where I can make a length of 18 and connect this base. Well, since A is longer than B, I would have to point it backwards, which would then break the reality that my angle A is 51 degrees. So if I try to do that, I find it's not possible. Okay. So based on this, we can then finish out this case. I'm going to go ahead and erase this unit circle, and we'll finish it out by saying angle B is now, we'll just call this B1 for the sake of consistency. We'll call this C1 and C1. So I have two angles. The third one I can find by noting that the angles add up to 180 degrees, which means C1 is simply 180 degrees, subtract A, subtract B1. So I know angle A is 51 degrees, angle B1 is what I just found here, so the angle C1 is going to be approximately, 97.8 degrees. And there we have it. So I can fill this in, 97.8 degrees, and my last piece of information is lowercase c1 for the side length. And I have the ratio, sine angle A over side length A, because I have both of those pieces. And now I have angle C, I can find this by setting up the ratios. Sine of angle A over lowercase a is equal to sine of angle C over lowercase c. And I would like lowercase c, so I'll multiply lowercase c over here, and I'll multiply the reciprocal to the other side. Now I'll fill in the numbers. Sine of capital C is going to be sine of 97.8 degrees. Now this is times lowercase a, which was given in the problem to be 18. And then sine of angle A was given to be 51 degrees. And since we approximately have this number, I'll say approximately. And then now lowercase c1 is approximately 22.95. Now, we have the last side length. and we have everything in the triangle. Now let's summarize. If you have information given in the form of angle, side, side, this is what we call the ambiguous case. Because as you're solving this problem, you will end up in a situation where you have sine of some angle is equal to a number. And we remember in the unit circle that if the y-coordinate, which is sine of b, is equal to that number, then there are two places in the unit circle where we can achieve that y-coordinate. The first, which we can label b1, is given by the reference angle. That's sine inverse of that number. And then the other angle, which is b2, is given by symmetry by saying this reference angle is the same as b1, and therefore b2 is equal to 180 degrees take away b1. So you can have up to two solutions in these cases. However, we remember that if angle A plus angle B plus angle C is bigger than 180 degrees, then you have an invalid triangle. Which case, you can use this to potentially eliminate one of the solutions you get. Now, what I just showed you is really all you need to know to solve the angle side-side case. But sometimes it helps to have a table of all the different cases that can arise from this so you know what you're looking for. So let's start with the case where angle A is less than 90 degrees. So we're going to have an acute angle A, and let's start drawing this. So I have an angle A right here, and I'm going to be given the side next to A. So we'll call that side B. Before I figure out what to do with side A, I'm going to think about the altitude of this triangle. So that's going to be h. Now I'm able to write down that sine of angle A is equal to opposite over hypotenuse, which is the altitude is now b times sine of angle A. And these are both pieces of information that are given. So let's imagine case number one, that the side length A that's given is less than b times sine of angle A, which means the A that's going to be given, this side length, is less than the altitude. Well, in that case, there is no way I can connect this triangle because A has to be longer than the altitude in order to make a right triangle there. So this, we say, no solution. Okay. Now, what if side length A is exactly equal to b times sine of angle A? So in that case, you would have A is going to coincide with the altitude h, which means I would draw side length A straight down, and then I would have a right triangle. In this case, I would have one solution, and that would be a right triangle. Now the third case is if A is bigger than b sine A, but I need A to be less than b. The reason for that we'll come back to later. So if A is bigger than b sine A, that means this is bigger than the altitude, because that's what the altitude is right there. Which means I'm able to connect the triangle right there, or connect the triangle right there. There are two possible ways I can do it, so I would say there are two solutions. Now, why did I have to put this caveat here? Because if the length A is bigger than the length B, and I try to connect the triangle this way, I will find that I will have to break the triangle in order to do it. So, if A is bigger than B entirely, then we don't have that option. We will only have a single option where we connect the triangle this way, and this side is longer than that side. This is going to be one solution. Now let's consider the other scenario, when you have A is bigger than 90 degrees. So we have an obtuse triangle on our hands, and we're going to be given angle A, and we're going to be given the side B. Now we want to use the side A to close this triangle. So if the side A, which is going to be across from angle A, is less than B, well, that can't happen, because in order to close this triangle, I need a side length that's at least as long as this, so that the long side is greater than the sum of the shorter sides. So in this case, we would have no solution. But if lowercase a is bigger than lowercase b, so that the side A is longer than side B, well, I can close the triangle this way, but I can't close it this way because that would break my angle A. So, no matter what, there is one solution. And there we have it. That's a summary of all the different cases that can arise from the angle side case. So in the world of solving triangles, we have dealt with the following types. We have the angle side and angle side angle, which we decided were actually the same thing. And then there was the angle side, the ambiguous case. In the future, we will learn how to solve the side and the side case. But for now, this is what we've done, and this is where we're going to leave it off. See you guys next time.